Okay, this is the video for Unit 5 Kinetics. We'll start with reaction rates. I'm going to try to do all 5.1 through 5.11 in this one video. So let's get started. Okay, first question. It shows us a table of a reactant of NO and O2 and the initial concentrations. I noticed right away here. 1 second. I noticed right away here. Make sure I have the right pen. That there is NO2, NO, and there's two of it, and then and so there's naturally there's twice as much concentration of NO, right? For every NO, for every 2 NO, right, there is 1 O2. And that's kind of seen in this ratio right here. This means that the reactants that are present, they're needed to react together. So for every 2 NO, 1 O2 is consumed. So if the NO graph drops sharply, right, like this, it kind of drops rather quickly, we know that O2 should kind of do the same. And this is an NO graph, and this is the O2 graph, right? It should do the kind of same because they get used up at the same rate. So definitely graph 2 is not correct, right? This can't be correct because this is getting used up, right? And this is getting used up even faster if you think about it, right? This is going even faster. This is happening over this amount of time, and you could say the other one is happening in half the time, right? It's happening even faster. So the answer is definitely not C, and definitely not D. And so let's see the answer choices for A and B. Graph 1, because the rate of O2 consumption is half the rate at which NO is consumed. 2 molecules of NO react for each molecule of O2 that reacts. Yeah, right? Because for every NO we react with, we use up half an O2. So every 2 NO we react with, we use up an O2. And B says, graph 1, because O2 molecules are consumed at a slower rate. No, O2 molecules are used up at a faster rate. So I would say the answer is A. Moving on. Oh, that was the whole page was a question? Yeah, this kind of tells you the whole story. Here, okay. Question number 2. Here they show us this equation. They show us that originally we have 5 grams of CaCO2 in both experiments, and then they cut the concentration of hydrogen in half, and then the temperature stays the same. So those are important things. This stays the same. This stays the same. And what changes is the concentration of H plus. Okay, so the key here would be the initial rate of formation of CO2 from the chemical reaction represented in the equation above in two separate experiments. The table provides the experimental conditions used. If both experiments are carried out with finely powdered samples of the solid and 50 milliliters of HCl aqueous, which experiment, if any, will have a faster initial rate of formation of CO2? Okay, well, this is, I think we went over this in class. Okay, so it says A, the rate of formation of CO2 will be the same because, no, okay, so if you have twice as much stuff, right, it can happen faster because there's twice as many H pluses going around. So there's, that much more H pluses around, it's much faster that something will bump into an H plus, right, when it binds. So it won't happen at the same rate because there's twice as much. How could that happen? If there's twice as many people on a field than there are normally, you're more often that you'll bump into somebody. So A is wrong, right? The rate of formation of CO2 will be the same because the surface area. No, it's not the same. The rate of formation won't be the same. Okay. CO2 will be formed at a faster rate because there are more H plus molecules going to react at unit time. I like C already. And then D, CO2 will be formed at a faster rate because the proportion of CO2 particles. Let's see, the proportion of CO2 particles is the same. The proportion of CO2 to H will be faster. Experiment 1? No, there's more hydrogens. Definitely not experiment 1. The answer is C. Okay, next question. When the chemical reaction of NO, 2NO plus O2 equals 2NO2 is carried out under certain conditions, what is the disappearance rate of NO? The rate of disappearance for NO is 5 times 10 to the negative fifth. What is the rate of disappearance of O2 on the same condition? So we already know that 1 is 5. So here's them telling you the recipe, right? So so this is what this means. Let me write it here. For every O2, you need 2 NOs to make 2NO2. That's all this tells you, right? So if we know that the disappearance of NO by itself, right, is 5.0 times, right, 10 to the negative 5, right? So this one disappears twice as fast. Because for every O2, for every one O2, we lose 2. So this one goes twice as fast, right? So O2 would be half as fast. So that would be the answer with 2.5. And now we could just fish for that answer. 2.5 times 10 to the negative fifth. So that's the rate. Does that make sense? And then if we fish through the answers, don't fall for this one, right? It could only be A. Okay, moving on. Which change will most likely increase the rate of reaction? Okay. So this is something you should have just memorized from the readings. So reaction is C2H4 plus H2 equals C2H6. So decreasing temperature doesn't. So decreasing temperature doesn't increase the rate of reaction. Think about it. If you want something to boil faster, right? If you want something to cook faster, which is a reaction happening, right? You don't want to lower the temperature, you want to increase the temperature. So decreasing the temperature doesn't do anything. Um, Adding a catalyst to the reaction, yeah, catalysts do. That's like adding oil, right? When you're cooking, when you add oil or butter, that increases the rate of reaction. C, increasing the volume of the reaction using a piston. Well, no. Well, if you increase the volume, that doesn't necessarily mean that the reaction is going to happen any faster. If anything, it might go slower. And removing H2 from the reaction system, that's not going to make removing something is going to slow the reaction down because there's less of it to react. So this one is pretty straightforwardly B, because catalysts, by definition, catalysts speed up a reaction. C2H4 plus H2 equals C2H6. C2H4 is reduced by H2 in the presence of solid platinum catalyst. So they're adding a catalyst here, represented by the equation above. Factors that could affect the rate of the reaction include which of the following? So changes in the partial pressure, of H2, changes in the particle size of the catalyst, and changes in the temperature for sure would change the rate of reaction, and pressure should too. So, for pressure, the higher the particle pressure means the higher the concentration. So if I put a lot of pressure, if you think about it, right? You ever heard of a pressure cooker? So like if you put your food in a pressure cooker, it ends up cooking faster. You ever put a lid when you cook something? That adds pressure. It makes it cook faster, right? So adding pressure does. So off the bat, we know the answer choices should have 1 and 3 in it. So off the bat, we can say it's not 3 only. It's not 1 and 2 because that ignores 3. It's not just, well, we don't know. It could be this. And it's not 2 and 3 because we know definitely 1 is right and we know 3 is right. And then the particle, now, is the particle size of the catalyst matter? I guess like if you use right, like let's say you use a stick of butter, right? You have your you have your frying pan, and then you use a little block, right, of butter. So you have your little butter on your frying pan, right? Is that going to do well for your meal, or is if the stick of butter starts to kind of like melt on the frying pan, will that do better for your cooking experience, right? It's better if it melts, right? Because then more of the surface area of the frying pan will be covered, and that'll lead to a faster reaction. So I would say it is E. So yeah, a lot of these examples, I use cooking because it's kind of intuitive, and it relates back to a real life phenomena, that you guys have experienced. I'm sure most of you have prepared some type of meal in your lifetime. Next example, we have this reaction of 5H2O2 aqueous plus 2MnO minus plus 6H plus turns into 2Mn 2 plus 8H2O plus 5O2, and the rate of disappearance is the rate of appearance was 1 times 10 to negative 3, and the rate of disappearance at the same time. So in this equation, for every 2, so here's the ratio, right? For every, I don't want to cross that out. So for every 2 MnO2, right there, they want to know the disappearance rate of this, right? The rate of disappearance. So for every 2 that are used here, what one do they give us for O2? O2 is produced, though. So this is produced at this rate, right? So for every 2 MnO2, right, we get 5. So we don't produce as much as we use, right? So it's 5. So we just multiply that by the rate, 1 times 10 to the third, negative third, and we get 0.4 times 10 to the negative third, right? Well, that's not really an answer choice, right? And if it's 4.0 times 10 to the negative third, we know this is definitely not it. And then, so what we're going to do is we're going to make this number bigger by moving this over to the decimal place one more step. So that's 0.4.0. And then we're going to make this a little bit smaller. So times 10 to the negative fourth. We move this one place over, and we move this one place forward, and it's the same number. This and this is the same number. Okay. Moving on. A kinetics experiment is set up to collect the gas that is generated when a sample of chalk consisting primarily of solid CaCO3 is added to a solution of ethanoic acid, CH3COOH. The rate of reaction between CaCO3 and CH3COOH is determined by measuring the volume of gas generated at 22 degrees Celsius and 1 atm as a function of time. Which of the following experiments is increasing the... Oh, okay. I didn't even need to read that. Not to sound crazy, but if it's asking us what's going to make gas production higher, I didn't even need to read all of this, right? Because, okay, let's see the options, right? Decreasing the volume of the ethanoic acid solution used in the experiment, less of anything doesn't make anything faster, right? Like if I have less popcorn or less what is it called? Kernels. I'm not gonna make more popcorn, right? So you having less of something doesn't make my reaction happen faster. So it's not A. Increasing the concentration of the solution, me watering something down, right? Decreasing the if you have juice, right, and the juice is really sugary and strong, right? Like and the reaction that'll happen in your body is that your body will feel more hyper from all the sugar. Watering down the sugar doesn't lead to the reaction in your body happening any faster, right? So B is not going to be the right answer. Okay. Decreasing the temperature. Decreasing the temperature never makes a reaction happen any faster. Okay. And decreasing the particle size. Okay. So let's say, yes. So let's say you have this big block of something, right? And you're cooking it. Let's say it's a big steak. Sorry, that doesn't look like a steak. But let's say whatever this is, you're cooking it, right? If I were to then break it up into these little pieces, right? It would cook faster, which is why people cut up their food when they cook it, right? Well, what's the point of cutting up food when you cook it, right? Is if you have these smaller pieces, right? It gets more time to cook each of its sides, get more time to cook, right? And this is increasing the surface area. So it's D. Okay. A 0.35 sample of lithium is placed in an Erlenmeyer flask containing 100 milliliters of water at 25 degrees Celsius. A balloon is placed over the mouth of the flask to collect the hydrogen that is being generated. Which of the following would increase the reaction rate between Li and water? So using 125 milliliters of water would increase the water, but that doesn't make the reaction happen faster. If I have a pot of soup, right? If let's say I have a pot of soup, right? Sorry, these are like all cooking examples, and I add more water, right? That does not make the soup cook faster. It's not A. Using a 0.25 gram. Oh, these are the same questions over and over again. Using a 0.25 gram sample of Li instead of no, that using less of anything doesn't make the reaction happen any faster. Cut into small pieces. I don't even need to, this was the same question. This is the same question. What does it do? Cutting it into small pieces, it increases the surface area. Relatively slow rates of reaction are associated with which of the following? The presence of a catalyst. Slow rates? No, catalysts speed things up. They make things go faster. Higher temperatures speed things up. When you want something to cook faster, you increase the temperature. Higher concentrations of reactions, that makes things go faster. Strong bonds with reactant molecules. That could slow things down. So strong bonds make it harder to break things down. Make it harder to break things down. So I think it would be D. Break things down. Okay, and then E is low activation energy. Low activation energy is like salt. It makes the melting happen at a lower temperature, right? So it's lower in the activation energy. That speeds things up. So the answer is D. Hopefully this is the last question. 5.1 is really long. Okay. The two molecules of Mg of equal mass are placed in equal amounts of HCl contained in two separate reaction vessels. Particle representations of mixing Mg and HCl and two reaction vessels are shown in figure 1 and figure 2 above. Water molecules are not included in the particle representations. Which of the following will initially proceed faster and why? So the reaction figure 1 will happen faster? No, this is the same question over and over again. At this point, I just want to look for which one is. It's definitely going to be figure 2, and it's definitely going to be because more of the atoms are exposed. So yeah, if it has more surface area, then the reaction happens faster. This is we've beaten this. If you've learned one thing from this chapter, it should be the smaller the pieces, the more sides of it that are exposed to things. Okay, let's go to 5.2. I'm not going to do the quick checks, just for time purposes. But if you need help with a quick check, you should do the quick checks. But if you need help with a quick check, I will gladly help you. But just for sake of time, because I'm trying to do all of chapter 5 at once. So here we're looking at the experiment was conducted to determine the rate law for the reaction. So A2 plus B equals A2B. And they did this with, if you notice, when I see one of these questions, I immediately start looking at the equation, and then I immediately start looking at the graph or the table or the chart, because that's where the information is. I don't care as much about reading like whatever other text there is, because even if you just like kind of look at the table and the chart, like it'll give you pretty much 9 out of 10 times it'll give you all the information you need to solve the whole thing. So all this says is that when you decrease the amount of B, you kind of decrease the reaction as a whole. Okay, so there's you should probably like so you want to write the rate law with this, right? And so you know that A2 in all of these stays constant. This pretty much stays the same. Well, let's look at here. This is where it stays constant. And so here it doubles, but the rate doesn't. The rate doubles as well. Okay, so here it's the rate is the constant, and then A2, and then B. And then, so if we look, right, answer choice A doesn't even take B into regard. So it can't be answer choice A. Right? And then B says that doubling both A2 and B2 would quadruple the rate of reaction. And that's not what happened. When we doubled doubling the concentrations of A2 and B will quadruple. That's not what we saw here. We saw that doubling this B caused it to double, but but also, okay, wait. Here, when A was the same and we doubled B, right? It doubled. So here it doubled. And then here, if we kept B the same, and then we doubled this doubled. So, doubling both would quadruple the rate of reaction. Right? 2 times 2 is 4. Since the rate is expressed as a tripling the concentration of A2, we don't know that. We didn't triple anything. We kept B constant and we doubled A. Then we kept A constant and we doubled B. And we saw that then regardless of what we doubled, it doubled. So we don't know about tripling. Since the rate law can be expressed as rate equals blah, 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 triple the doubling the concentration of B will keep the concentration of A2 constant while doubling the rate of the reaction. Okay. Doubling the rate of B will double the rate of. But that's not what this says, right? That's not written correctly. So doubling a first order reaction doubles the rate. If both reactions are doubled, it creates a fourfold increase. And so we don't. This was written wrong, but the rest of this is right. Doubling the concentration of B while keeping. Well, that's what we did here, right? We doubled the concentration of B while keeping this the same. Will double the rate of reaction. But the correct answer is B, because, anyways, I explained this. Next question. In aqueous solution, the reaction represented by the equation above has the experiment determined rate law of S2082 and I negative. If the concentration of S2082 minus is doubled while keeping I constant, then what happens? So we know that this says right here, just to break this down for you, this demonstrated rate law says that the rate is tied in, right, to, this kind of tells you the pace of it, right? And so this says that if this is doubled, right, there's a 2 at the top, if this is doubled, and iodine is constant, it doesn't change, then the rate will double. So things will happen faster. Then okay, so Um, so the rate of the reaction will remain the same because K will decrease by half. Not necessarily true, because there's nothing that indicates K being half. K doesn't change unless temperature changes. And then B says the rate of reaction will double because so this is what this is trying to say is that the rate will double because S208 will double. That means S208 controls, it's proportional to S208. The rate of reaction will increase by a factor of 4 because 2 moles of SO42 will be produced for each. No, this doesn't mention SO42 at all. The rate doesn't. The rate law doesn't. The rate of reaction will increase by a factor of 4 because the reaction is second order overall. No. Answer is B. Things are tied to this. So the overall order tells you what's relevant. So here, it's a first order reaction, so the rate only doubles. Okay, this looks familiar. 2NO2, 2NO plus Cl minus equals 2NOCl. Laptop's dying. What can I do? Well, I guess we'll take a pause from the video if my laptop dies, because I don't even have another port to charge. Okay, so 2NO plus Cl2 turns into 2NOCl, and there's 3 experiments, and we see that in the first experiment to the second experiment, we double the amount of Cl. So this is how you should read these things. Look, it stays the same here, right? But then we double here, we times 2 here. And what does that do? That doubles the reaction. And then we kept things, we kept things same between 1 and 3 for Cl, right? And then we doubled NO. And what did that do? That, I think, quadrupled the reaction. And so the initial rates of the reaction presented by, and because the rate doubles from 1 to 2, this is the first order in Cl2. So the rate law here would be that NO would quadruple things, and Cl would double things. So sorry, my handwriting isn't the best. Would be K, and then we would have NO. But because when we doubled NO, not NO2, sorry, I don't know why I keep writing NO2. NO, then because it's exponential when we doubled it, right? When you double something to 2, and then it goes to 4, it's exponential, right? So you put a 2 up here, And then because Cl, it would just be Cl2. Cl2. Right? And so the only one that has that is D. Because the initial rate quadrupled when NO was doubled, and doubled when Cl was doubled. That kind of describes exactly what happened here. Okay. The rate law for the reaction of nitrogen dioxide and chlorine was found to be KNO2 squared Cl2. By what factor does this? So doubling NO2 is second order because of this exponent here, right? It is second order, but Cl is first order. That means doubling Cl will be leading to double. So if the factor of the rate change for both are doubled, right? So if you double something, right, and then it has a factor of 2, and the other thing would just double, you have 4 times 2, and that it would multiply by 8. Sorry, I'm kind of racing against time because of my laptop might die, and I only have 2 ports, one for my tablet and one for hooking up to this monitor. Okay, so next question says, has this table. It shows us that we keep O2 the same and we double NO, and that doubles the reaction. And then we keep NO the same, and then we quadruple the O2. Why are we quadrupling the O2? When we increase it by 4, that increases it from 8 times 10. So basically, this is one factor bigger. So let's say this is 80, right? Because it's one exponent bigger, right? And so this is then would be 5. So 80 divided by 5 equals 16. So when we quadruple this one, it increases by 16. Oh, so this is kind of easy. So it would be NO just when you double NO, it just doubles. But when it's first order. So here we could just write a rate, right? And that equals K. And so when you double NO, it's just doubles. First order. But O2, right? Because think about it, 2 to the 4th is 2 times 2 times 2 times 2. It's the second order, right? And that equals 16. So that would be O2 squared. Okay. Okay, I'm going to pause the video here because my laptop's about to die, and I'll upload, and then I'll make a part 2.